Born-Openheimer approximation is a mathematical approximation in quantum mechanics that assumes the wave functions of electrons and the atomic nuclei in a molecule can be treated separately. This approximation is basically based on the fact that the mass of an atomic nucleus is much larger than the mass of the electron. So the nuclei move much more slowly than that of the electrons. This Born-Openheimer approximation in quantum mechanics, quantum chemistry, and molecular physics, this approximation is best known mathematical approximation in molecular dynamics. Especially, it is the assumption that the wave function of the atomic nuclei and electron in a molecule can be treated separately. Based on the fact that the nuclei are much heavier, much massive than that of the electrons. And due to the larger relative mass of the nucleus compared to the electrons, the coordinates of the nuclei in a system are approximated as fixed, while the coordinates of the electrons are chosen dynamical. The approach is named after Max Born and his 23-year-old graduate student Oppenheimer. And this approximation is widely used in quantum chemistry, especially to speed up the computation of molecular wave functions and other properties of larger molecules. Certainly, there are cases where the assumption of separable motion no longer holds, which make the approximation lose validity. But even then, the approximation is usually used as a starting point for more refined methods. This Born-Openheimer approximation makes it possible, at least, to separate the motion of the electrons and the motion of the nuclei, and it certainly forms the basis for most electronic structure methods. This approximation involves the assumptions that I'll try to confine them here. I mean, the electronic wave function, it depends upon the nuclear position, but not upon their velocities. The nuclear motion is so much slower than electron motion that they can be considered to be at rest, they can be considered to be fixed. And the nuclear motion, for example, if you take into account rotation, vibration, they see a smeared out potential from the electrons. And this Born approximation is widely used. It's used in most of the domains of molecular physics. And at the same time, this approximation breaks down when we consider two or more excited electronic states, which are energetically close or have non-eligible, non-adiabatic coupling at some point. In this video, I'll be talking about Born-Openheimer approximation. And when we are supposed to deal with molecules, and if I choose the simplest, say I choose hydrogen molecule. This hydrogen molecule has two nuclei, and it has overall 2 electrons. There's a cloud of electrons. And if we want to solve this problem, and if we have to calculate the Hamiltonian of this problem, what we have 2 nucleuses and we have 2 electrons. So there will be a range of interactions involved in this problem. And if H is a representative of the overall Hamiltonian for this system, then this H of psi should give us E of psi. So what we have here? We have here 2 nucleuses and we have 2 electrons. And we are choosing the simplest, and that's hydrogen molecule. And if we have to think about the Hamiltonian of this system, that will contain the kinetic energy of electrons, and that will contain the kinetic energy of nucleuses. Now, in a molecule, we can have more than two nucleuses. So we have to take into account the kinetic energy of these nucleuses. We have to take into account the kinetic energy of the electrons that are involved in the overall system. And we have to take care of the potential energy between electrons. So whatever the number of electrons is, we have to calculate the potential energy between these electrons by virtue of the electrostatic repulsion that will exist between these electrons. And the potential energy between the electron and the nucleus. And the potential energy between nucleuses. So we can see that this Hamiltonian for if I assume that I have a molecule and this molecule has electrons and it has nucleuses, it's an overall system, then I have to take into account the kinetic energy of the electrons, the kinetic energy of the nucleuses, the potential energy between the electrons, the potential energy between electron and nucleus, and the potential energy between nucleus and nucleus. And to be precise here, to be logistic, I mean, quantum mechanically, we can have the energy of the molecule is quantized. If we check this molecule experimentally, we can calculate the energy that's linked with the molecule, and we can find out that these energies are quantized for molecules, like that of an atom. But the solution of Schrödinger equation for a molecule is it's very difficult. It's very complicated from that of an atom. And what could be the reasons? I mean, if we compare this situation with an atom, I mean, in case of an atom, we have to only solve the Schrödinger's equation for one optical electron. If we have an atom having many electrons in it, and we can solve Schrödinger's equation for the optical electron, the electron that's available in the outermost orbit of the atom, and so the Hamiltonian of the Schrödinger's equation that contains only the kinetic energy and the potential energy of this optical electron, avoiding the inner electrons, because the net impact on the system happens to be zero. But when we talk about a molecule like, say, hydrogen atom, or any molecule which has more than one nucleus, what we have to take two or more nucleuses and containing these number of electrons in a bound state. Now here, the molecule also interacts via the nuclei. I mean, there is interaction between the nucleuses of this molecule, and nuclear motion in the molecule cannot be ignored, as is the case in case of the atom, where the motion of the nucleus is assumed to be ceased because the mass of the nucleus is very large in comparison to the mass of the electron. So obviously, this quantum mechanical Hamiltonian operator that we have for a molecule containing all these terms that we have kinetic energy of electrons, we have kinetic energy of the nucleuses to be taken into account, the potential energy between electron and nucleus, and nucleus and nucleus. So here, the Schrödinger equation for a molecule, we can write down the Schrödinger's equation. I mean, we have the Hamiltonian, and we can write down the Schrödinger's equation for this. So if I write down in more precise way the Hamiltonian for this molecule that has been considered. So if I choose, I have H, and what it will account for kinetic energy of all electrons, kinetic energy of all nucleuses. So choosing J as the number of electrons, say for example, we have kinetic energy as h cross square del J square by twice me, where this me refers to the mass of the electrons, and J is chosen as the overall number of electrons that are present in the molecule. And then we will have the nucleuses, the kinetic energy of the nucleuses. So for that we will write h cross square delta I square by twice mn. Let me use, okay, I will be the right choice. Okay, so this will give me the potential, the kinetic energy between the nucleuses. And then what we have potential energy between electrons, we have potential energy between electron and nucleus, and we have potential energy between nucleus and nucleus. So I is a representative of number of electrons here, and J represents number of nuclei. So moving on from here, we have the Hamiltonian, and we have all the symbols that we have inculcated here. I would like to repeat their names. H cross is the reduced Planck's constant. Me is the mass of the electron. Mi refers to the mass of the nucleus, and VEE, it refers to the potential energy between the electrons. VEN is the potential energy between electron and the nucleus, and VNN is the potential energy between two nucleuses. So what we have H psi equal to E psi. This is the Schrödinger's equation, and H has been definable. Now, if we look at this equation is complex. I mean, it is so complex that the Schrödinger's equation for an atom, that's the simplest case. But talking about the situation that we have here is that for an atom, the Schrödinger's the solution of Schrödinger's equation is simple. So if we look at the Hamiltonian of the molecule, it seems like the solution of this Schrödinger's wave equation is impossible. I mean, it's not possible. It's not possible to solve this Schrödinger equation. And in order to get some approximate solution of this problem that has been launched here for a molecule having nucleuses and electrons, it was Born and Oppenheimer. And what they did, they proposed a quantum mechanical approximation here. So they came up with quantum mechanical approximation. Now, according to it, the motion of the electrons inside the molecule. So we have a molecule having, say, nucleuses, and we have electrons in this molecule. And according to this approximation, what is assumed here is that the electrons in a molecule, inside a molecule, at any instant, their motion is constant. And it is same as if the nucleuses were fixed. These electrons have the motion, their motion is constant, as if the motion of the nucleuses that are present in that molecule, they are fixed, they are at rest. Now, according to this statement, what they did is that they showed that the nuclear Schrödinger equation can be, molecular Schrödinger equation that we have here, this equation can be solved, and it can be solved into two steps. And what are these two steps? So we can think of, so we have H of psi equal to E of psi, and we have already defined H. But if I rewrite this Hamiltonian, that will be the right thing. So if I rewrite it as sigma J H cross square del J square by twice me plus sigma H cross square del I square by twice mi plus VEE plus VEN plus VNN. So what is proposed here is that we have a system, and in this system we will have a state vector, we will have a wave function, say wave function 1, and we will have another wave function, say wave function 2, such that the overall wave function for the system will be the product of psi 1 and psi 2. This is the approach. So we will have independent wave function for one state, and we will have independent wave function for another state. Obviously, if we have electrons here, and we have electronic wave function, and we have the nuclear wave function, that will automatically go with the numbers that are being used for the wave function, psi 1 and psi 2. So what will be the first case, the first step? The first step is going to be this h of psi e equals E of psi e. So what we have a molecule, and we will subject this molecule to the mathematical treatment, and we will calculate its Hamiltonian in terms of Hamiltonian for its electrons with respect to the wave function psi of e, and we will separately deal with the nuclear system of this molecule. So the very first step would be h of psi e, where we will have the eigenvalues for the system. And in this step, what we do, we calculate the energy due to the electron motion in a molecule. And assuming that the nuclei, they are at rest, and we calculate the Hamiltonian. We operate this Hamiltonian or a wave function of electrons, and we obtain the energy eigenvalues. And so what is, in order to elaborate this thing, I mean the wave equation for the electron motion is solved alone, independently, in which nuclear coordinates are fixed. So nucleuses are assumed to be fixed, and the solutions are assumed to be in the fixed position of the Schrodinger's equation for the motion of the electrons. And then the next part, so if I write down this Hamiltonian as He for electrons, so this He will be comprised of this term, and it will be comprised of this term, and it will be comprised of this term. So I can write down this Hamiltonian. So He is going to be sigma j h cross square del j square by 2me plus vee plus vne. So on solving this Schrodinger's wave equation for the electron motion, we will come up with energy eigenvalues, as we know from the basic course of quantum mechanics when we solve the problems like hydrogen atom. So we will have E here. Now we will have E electrons as the eigenvalues. And now what would we do in the next part is we will choose the Hamiltonian for the nucleus, and this energy eigenvalue for the electronic motion will be added as a number to this Hamiltonian, and operating this on psi will give me E psi. So what are we doing here is that the value that we have calculated for the motion of the electrons, its value is incorporated into the Hamiltonian of the nucleus to get the overall solution of the problem. And here we can think of HNN. So this HNN is going to be what? It's going to be, this is sigma h cross square del I square by twice mi, and plus Vnn, and then plus En, which has been calculated for electrons. Psi is E psi. All right. So what we have is that now we will be calculating the Hamiltonian for this overall system carrying nucleuses and electrons, and we will have a Schrodinger's equation in this formalism by making use of Born-Openheimer approximation. And And on calculating the Hamiltonian over the wave function psi, we will be able to calculate the quantized values of energy for this molecule. And this energy will come out to be the energy of electron, what's called as electronic energy, plus vibrational energy, plus rotational energy. So this EE, this energy is due to the electronic motion inside the molecule. And this EV is the vibrational energy due to the vibrational motion of the molecule. And this ER is the rotational energy, and this rotational energy is due to it is due to the it is due to the rotational motion of the molecule, to be dependent on, if I take a diatomic molecule, these nucleuses can vibrate, they can have vibrational energy, and they can have the rotational energy with respect to their center of gravity or center of mass.